Welcome back to Tech Notes. In this video, we're going to talk a little bit about some HVAC terminology that you're going to use troubleshooting and when you talk to tech support lines. And it's nice to always have those answers in advance. So, as you diagnose equipment and read technical manuals and talk to technical field representatives, there's some terminology you should know. Not only should you know it, but you should know how to use it in equipment diagnosis. Even if you'd never have to talk to a technical rep, these are all things you should be able to do and do when you diagnose either air conditioning or refrigeration equipment. Now, in this video, I do have some examples that I'm showing you of equipment that I've diagnosed in the field and readings I've taken. Now, this is all on air conditioning equipment. I will probably do a separate video on refrigeration equipment because it's a little bit different. And I'll try to get that as we go through here. Now, let's start off with target pressures. Most manufacturers publish target suction and discharge pressures for a specific model number of units, okay? They're many times found inside the wiring compartment, or you'll also find them in the installation manual. This is just a clip out of a Linux installation manual. So in this video, I've used a lot of examples from a piece of Linux equipment. It's their 14 HPX-036. It's a 3-ton heat pump. And we were dealing with temperatures probably around the 80 degrees point. So when we look at this, our target pressures, 276 on the liquid side, 142 on the suction side. That's our liquid and vapor. Okay, and we were obviously in cooling mode. If we were in heating mode with lower temperatures, you'd have different target pressures. Again, these are targets, okay? It's what the system is designed for. There are going to be some minor variations based on the installation you're in. Okay? The next thing we're going to look at is the target evaporator, or DTD, design temperature difference. It's the temperature the evaporator coil should be based on the return air temperature. Okay? Air conditioning about 35 degrees below ambient, or in the case of a refrigeration system, about 10 degree below the box on a walk-in, 20 degree below the box on a reach-in. Okay, so for example, a typical AC system with a 75 degree return temperature, the design temperature difference would be 35 degrees, which means the evaporator temperature should be about 40. The DTD, the design temperature difference, will definitely vary based on airflow and evaporator size. Now, that was the design. We also have a measured temperature difference. It's the suction saturation temperature, not pressure. So you take your pressures and convert it to temperature, as measured on the suction gauge for the refrigerant, then can be compared to the box or return temperature to calculate your measured or actual temperature difference. Here's an example. Okay, the blue circled numbers are the ones we're talking about. So in this case, I measured a return or supply air temperature of 69.7 degrees. Okay, that's not the one I want. I want the return air temperature, which is the 75 degrees. Okay, be careful because you're a lot of times tempted to take the 69.7, the blue circle, and it's reality you should be using the 75 because it's the return air that we want to see. Okay, so I have a 75 degree return air. I have a 34 degrees evaporator temperature because, again, the testo gauges that I use the smart probes, automatically convert my low pressure to the evaporator temperature. Okay, so I take my 75, subtract the 34, and my temperature difference on this system is 41. So that's my evaporator temperature difference. Okay, 35 design, 41, I'm 6 degrees off. Okay, start of a problem. Now, we also want to look at the target condensing temperature over ambient. This is the target temperature, the liquid saturation, as measured on the gauges. It should be above the outside air temperature measured in the shade entering the condenser coil. If you don't have any shade around, you take it of the air entering the condenser coil. This will be 30 degrees over the ambient on older units, and it can be as down to as low as 15 degrees on newer high efficiency units. This is the liquid line only. The discharge line will be much higher temperatures. So be careful on where you take this. You want to take this on the liquid line right as it is exiting the unit. We're also going to, so the target condensing temperature is the outdoor temperature plus the condensing temperature, okay, is my target condensing temperature. So if my outdoor temperature is 95 and I have 15 degrees CTOA for a 16 SEER system, my condensing temperature should be 110 degrees. Okay. Condensing temperature over outdoor air. This is again from the same system we just looked at. Condensing outdoor air temperature was 76.6. Condensing temperature 76.8. I have a 0.2 degree difference. Obviously, we have a problem. Okay. Start thinking about all the readings that I'm showing you here, because we'll talk about what the problem is when we're done. Target superheat. It's a superheat you should have, and it varies based on if the system has a TXV or a piston metering device. If it's a piston, you must use a superheat chart as well as a thermohygrometer or psychrometer to measure the indoor wet bulb and dry bulb, because these charts require these readings. If it's a TXV, then you can set your target at 5 to 15 degrees if measured inside and 10 to 20 degrees if measured outside. Okay. Measured superheat is the increase of the suction line temperature when compared to the saturation. So in this case, I have a superheat. Okay, my suction line temperature, I measured at 76.1. Okay. My evaporator temperature is 34. My measured superheat is 42.1. This is way high. Okay, we have a serious issue here. Target subcool is the subcooling you wish to achieve. Many units have this marked on the data tag. If not, then use 10 degrees subcool on a TXV system and 5 to 15 degrees on a piston system. Recognizing that on a piston system, this rule will not always apply. Okay, so again, be careful with subcooling, okay? Look it up. The manufacturers will tell you what the correct one is. So in this case, we have my heat pump, okay, that I have. It's a 3-ton heat pump. I also have a 3-ton air handler that's part of the matching list. My target subcooling in the cooling mode is 5 degrees. This comes right off the equipment, the inside of the electrical cover. Okay, so I want a 5 degree subcooling. The measured subcooling is the difference between the liquid line temperature and the condensing temperature, the liquid saturation temperature from the high side gauge. Again, make sure you take your temperatures on the liquid line only, not the discharge line. So in this case, I have a subcooling that I've calculated. My liquid line temperature is 78.4. My condensing temperature is 76.8. Now we have a problem here, okay? Because my condensing temperature should be over my liquid line temperature, okay? Because my liquid line temperature has the subcooling. Okay, these values really should be reversed. In this case, this isn't going to work because I can't have a negative subcooling. Okay, there's a serious problem in this system. Okay? So we know superheat was high, subcooling is very low, okay, and my condensing temp, okay, is way off as well over the outside air. Okay, it was 6 degrees off. Outdoor ambient is the outdoor dry bulb temperature in the shade entering near the center of the condenser coil. Okay, now, in this case, the whole thing was shaded, so it really, I mean, I'm taking my outdoor ambient probably in a little bit of a wrong place. But Okay, I'm taking it right there because, again, the whole thing was shaded. It was all about the same temperature, and it was just a handy place to put the gauge down. Okay. Outdoor ambient came out to be 76.6 dry bulb, 73 wet bulb. Now, we're going to go take a look at the inside systems. The return dry bulb is the return air without taking evaporation or humidity into account. It's best taken in the return right before the unit, and just don't lay your thermometer in the space. So return grill, return line right as it comes into the unit. In this case, return dry bulb, 75 degrees. Okay. Return wet bulb is the temperature of the return air plus the evaporative effect. It's going to be lower wet bulb temperature when compared to dry bulb, means low relative humidity. If the wet and dry bulbs are the same, it's going to be 100% relative humidity, which means it's going to be basically raining in the space. It's best taken in the return, again, right before the unit with the fan running, not in the space. Okay, return wet bulb, again, I use the Testo toolkit, shows right up there. My return wet bulb, actually, let me undo that because that was not the number I wanted to. Let's go back, circle the right number. Okay, my return wet bulb, 62.7. Okay, so I had a return temp of about 75, and that was going down a little bit because the system was running. If you remember, my last reading was 75. Return air dry wet bulb is 62.7. Okay, now I do have a return air relative humidity. We'll talk about that in a minute. Return relative humidity is the relative humidity of the air in the return. Relative humidity is the percentage of moisture in the air compared to how much moisture is in the air. Hot air can hold more moisture than the same air at lower temperatures. So again, I have a return relative humidity of 51.2%. Now, careful, because the supply air has a relative humidity too, and you would think because your air conditioner is supposed to be dehumidifying, my supply air relative humidity would be lower. That's not the case. Okay, supply air relative humidity, unless you're running a dehumidifier, is going to be higher. Target supply air temp is an air temperature calculated using a delta T chart comparing the return air dry bulb and the return wet bulb temperatures. Target supply air temperature is the dry bulb and can be compared to the return dry bulb to calculate the target delta T. Don't confuse target delta T or evaporator split above the delta T with air temp split. Keep in mind that the 18 to 22% rule that many use only applies to homes with 45 to 55% relative humidity. As the relative humidity goes up, the target temperature split will go down. As the relative humidity goes down, the split goes up, because a good portion of what your air conditioner does is dehumidify. So as there's more humidity to pull out of the air, we're not going to cool the air as much. The delta T also varies based on airflow, with higher airflow flows resulting in lower delta T. The longer the air sits on the coil, the more it's going to dehumidify and cool. So this is just an example of airflow across the indoor coil. Okay, actually comes out of a Lennox equipment manual. Okay, so if I have a return air dry wet bulb of 65, okay, across the bottom, and I have a dry bulb of, let's say, 75, let's go to 74, but 75 would be, okay. So you're going to see where the two lines meet, and in this case, 65 wet bulb, 74 dry bulb, I'm going to have a delta T of 16 degrees. Okay. Now, if we take a look at this example here, my return bulb coming in is 72 degrees dry bulb, 64 degrees wet bulb, and leaving on the supply air of the system is 53 degrees. Okay, they have a delta T of 15 for those numbers, so this system is working properly. Okay, so again, the rule of the 20 degree delta T, 15 degrees delta T doesn't always work out. Because again, if I have 80 degree return air, okay, with 57 degree wet bulb, my delta T could be up in the 20s and could be perfectly okay. But if I have 70 degree return air and 70 degree wet bulb and I have a delta T of 10, that could be perfectly fine as well. So it is critical to use the airflow, the actual delta T charts that you find. You can find these just about any place, but a lot of times they're in the manuals. So the measured delta T is the measured difference between the supply and the return air dry bulb. Okay, keep in mind it needs to be taken a few feet before and after the unit to allow air mixing and to reduce the radiant gains and losses. Okay, you don't want to take it within a direct line of the coils, or if you're doing it in a heating system, don't take it within the direct line of the heat exchanger because you could pick up radiant heat. Okay, so in this case, I have a 69.7 supply, 75 degree return. My delta T is 5.3. That does not work out. So delta H is an advanced measurement that calculates the change in enthalpy or the heat content of the air between the return and the supply. You can do this with two digital thermohygrometers like the 605i in the smart probes, and it considers temperature and humidity of the air entering and leaving the evaporator, because that truly tells us how much heat we're recovering. Okay, and that translates into the delivered capacity. The delivered capacity is the calculations of BTUs of heat being removed from the airstream, which combines the delta H with the CFM of the air to give you the total work being done across the evaporator coil. This is the true measurement of whether or not a system is working properly or not. So in this system, okay, a 3-ton system with all the measurements that I took, the delivered capacity is 13,361 BTUs per hour. Now, 3-ton system, okay, we have 12 times 3, so that should be giving us 36,000 BTUs. So we obviously have a problem because that's not being given. The discharge temperature, jumping real quick back outside, is the measured temperature of the discharge line leaving the compressor, not the liquid line. The discharge temperature you can use to calculate how much heat, okay, how much of a subcooling, or sorry, superheat you have when it comes out of the compressor. Tells you a lot about refrigerant flow. Target liquid line temperature you can use when checking the system without the gauges. The target liquid line temperature is the target condensing temperature minus the target subcool. Okay, it's usually measured right at the condensing unit. Okay, so again, you go into the manuals, you find the target condensing temperature, pressures converted to temperature, okay, and then you can find the subcooling, and you can check the liquid line temperature at the condensing unit. Target suction line temperature, again, the target suction temp is the target evaporator temperature plus the target superheat. It's most accurate when measured inside, but it's also valuable when measured outside. It's going to be a couple degrees difference. The approach temperature is just another name for the target liquid line temperature, basically, and it's a reading that Lennox publishes for many of their units in the installation manual and on the back of the panel of the condensing temperature. Systems with larger or more efficient condenser coils tend to have a lower approach, cooler liquid line, than those with smaller or less efficient coils that tend to have a higher approach, warm liquid line. Okay, liquid line temperature minus compared to outdoor temperature. This case we have an approach temperature of 1.8. Now again, this is really sort of backwards, okay, but the approach temp is 1.8. Now, this system has a 6-degree approach temp, so obviously we again have a problem. Suction line temperature difference is the temperature rise between the inside after the evaporator coil and outside by the condensing unit. When a suction temperature difference is more than 10 degrees, compressor overheating or oil carbonization can occur. So again, we don't want to have massive temperature rises. So in this case, I have an outdoor suction line of 76.1 degrees. I have an indoor suction line reading of 75.2. I'm way under 10 degrees, but this line is way too warm. Remember, our superheat was very high. Just like the suction line temperature difference, the liquid line has a temperature drop. It's the difference between the liquid line temperature outside by the service valve and inside before the metering device. Ideally, the liquid would have a very little temperature drop, and any drop of more than a few degrees should be looked into. Long line lengths, vertical risers, running the liquid line through a low ambient space. Contact between the liquid line and suction line or other restrictions can lead to higher than normal liquid line temperature differences. So again, in this case, I have a liquid line temperature of 78.4 outside, and inside, this is 75.4. That's 3-degree difference. Okay, am I really worried about that right now? No, because the system itself is not running properly. We have some pretty serious issues with my condensing temperature outside being too close to ambient. Okay, and remember, we had capacity issues. Also, I have a 42.1 degree superheat, which isn't right. Now, we also have some airflow issues we have to look at. Static pressure. It's the positive or negative pressure exerted on all surfaces equally within a duct system. The static pressure does not mean measure flow. It's like the pressure inside a balloon that inflates or deflates. Static pressure is measured in inches of water column in the US. Inches WC. Design total external static pressure, both positive and negative for a particular furnace or air handler, are designed to work under external to the appliance. Most residential units are designed for 0.5-inch water column. Okay, blower performance and airflow changes with the static pressure. So if we look at it, the inside of a manual, for example, the air handler that I've used for my examples in this, okay, we have blower performance. Remember, I have to have 400 CFM of air per ton of air conditioning, okay, for proper cooling. Okay, so my design static is 0.5. Okay, so if I'm running my blower at high speed at 0.5, okay, static pressure, I'm going to get 1250 CFM of air being moved across that coil. Now, as my static pressure goes lower, I can move more air. Obviously, the opposite is in effect. Okay, if my static pressure goes higher, I'm not going to move as much air. Now, this is measured with a dry coil. Okay, this is a dry coil. Once my coil gets wet, my static pressure, the pressure drop across that coil is going to go up anyways. So static pressure is extremely important to a system because, again, if you have a specific airflow at that design static pressure, okay, and you change that, you go over that static pressure, your system is going to move less air and eventually is going to move less air than required for proper cooling or heating. So to measure the static pressure, okay, you use a manometer or magnehelic gauge along with static pressure tips. On a furnace, this would be measured inside the furnace before and after the blower, but before the coil. In an air handler, okay, it's measured before and after the unit in the ductwork. The total difference between the negative and positive readings is my total external static pressure. So if I have a 0.2 return and a 0.3 supply, I have a 0.5 inch water column total external static pressure. Easiest way to think of it, add the two numbers together, drop the signs. You're using the absolute values. So in this case, I have a 0.21 inch, okay, and a 0.05 inch. My 0.21 is in the return. My 0.5 is in the supply. Now, there is a warning, there's a little warning that goes off here also, because this is a pretty big difference between the two, okay? But again, I have a 0.21 return, 0.05 inch supply. Okay, so this here is a positive, and you look and see this is a negative. Well, I don't care about that. I'm going to drop the signs and add the two numbers together. For my 0.26 inch total static pressure, okay, I'm going to take my absolute values, 0.21, 0.05, 0.26, gives me my total static pressure. Now, that's under the 0.5 that's required. Okay, so again, if I go back a few slides, I think let's see. Okay, if I go back here, I'm right about here. So with a fan running even on medium, I am moving my 400 CFM per ton for my 3 tons. So again, lower static pressure, as long as we're cooling properly, I'm okay. Static pressure drop is the measured pressure change across any portion of a system. For example, I'll have a pressure drop across the coil. I have a pressure drop across a filter. I'll have a pressure drop across any ductwork. It's helpful in diagnosing airflow issues and changes over time. Remember, pressure drop is a comparison of one location to another. So, a dirty coil, okay, if the coil's dirty, it's going to have a higher pressure drop than a clean coil. If a filter gets dirty, it's going to have a higher pressure drop than a clean filter. So if I can't see what my evaporator coil looks like, but if I have access to the manual for that coil, and if I have access to a pressure reading before and after, I can tell you if that coil's clean or dirty. Same thing with filters. In building automation, I can use the static pressure drop of a filter, okay, to tell me whether or not those filters are dirty without sending someone on the roof to look at them all the time. Pressure drop will change over time as airflow changes. Now, before I wrap up the video, I want to show you a couple things on the manual. So I want to drag a manual over here. Okay, this happens to be the manual of, okay, the Lennox manual found for the air handler I was looking at. Okay, this is the product specifications. Okay, tells you how to read the model numbers. Okay, so here we have, okay, I can look and see what the model numbers are. Okay, the cooling capacity. Okay, they always put that on the front. Okay, and then as you go through here, it tells you optional accessories like electronic heat, tells you design for replacement circuit breakers, and then for every unit that's part of the thing, this is the one we're looking at, okay, it tells you all the different numbers, electrical data, okay, what the blower output is, what the filters are that are internal to the unit, okay, tells you all about the coils, everything you would need from an engineering standpoint. But from a technical standpoint, okay, we're really worried about the blower performance, okay, is what we're really worried about. Okay, so if I want to find my 3-ton unit, which is right here, this is the chart that I showed you, okay, and again, the 0.5 is the highest because that's the highest this unit is designed for. Okay, and it tells you about the different heat strips and electrical data. Okay, tells you what the blower under full load amps is. Okay, so amperages gives you a lot of technical information on that. Okay, tells you about airflow, tells you how to build a return plenum. Okay, so all of this is pretty important. Now, the outside unit, the condenser, has similar things with the manuals. Okay, tells you dimensions, tells you all the piping diagrams inside, tells you how to read the model numbers. Okay, again, that once you start getting used to them, you're actually you can pretty much see them without having to look it up all the time. Okay, tells you how the service valves are put together. It even gives instructions how to recover refrigerant properly. Okay, tells you what not to do with unit placement. Tells you recommended line set lengths. Okay, so we had the 036 here. Okay, this says recommended line sets could be 15 to 50 feet. Okay, and tells you if installing longer than 50 feet. Now this right here, okay, this is where our problem was. So remember I said, remember all the numbers we were talking about? No one took the extra line set. There was a 250 foot line set on this one. Okay, no one took that into account. Okay, it tells you how to braze it properly. So the install manuals are actually pretty important as you go through these systems. Where I want to scroll down, and I'm going to scroll down here real quick because it does pass the wiring and everything else like that, gives you the airflow again. Okay, but it also gives you the target subcooling and everything for the different units. Okay, remember I was using the 036 as my indoor unit. So again, we find the outdoor. Okay, and I had my 5-degree subcooling. Okay. It also tells us for the different units I told you about the liquid and the vapor pressures. Okay, it even gives you a pressure drop here so you can say, okay, what is it? Okay. The other manual that's sort of important, again, is, well, basically same thing. This is just the product specifications. So all of this comes into play with the troubleshooting you do in a system. Okay, again, if you would get your indoor temperatures, your wet and dry bulb, your outdoor temperatures, pressures, outdoor ambient temperature, and line set temperatures in both locations, you can troubleshoot just about any problem. Please remember, if you haven't already, please take the time to click on the subscribe button that's right below this video. Subscriptions are pretty important to us that do YouTube recordings.